briefly introduce a paper focusing on ram pressure stripped tails that Greg Bryan and I wrote that went on the archive recently. It compares a mixing-driven model of stripped gas acceleration to simulations and looks into some of the impacts of mixing on the gas in the stripped tail. First, a primer on ram pressure stripping. It was introduced almost a half century ago as a contact force per unit area, pushing gas out of a galaxy, and is often assumed to be instantaneous. This means that at any time you can simply compare the ram pressure to the restoring force to determine if gases will be stripped. But this is a hydrodynamical interaction, so we decided to come up with a very simple mixing model for gas acceleration from galaxies. We used energy and momentum conservation and some simple assumptions detailed in the paper to come up with a gas velocity that is dependent on the fraction of gas from the ICM that mixes into the galactic gas, here denoted as FICM. On the right, you can see that using this model, we would predict gas to lie along one of the grayscale lines in the velocity FICM plane, which may vary due to an increased wind velocity or increased escape velocity. We test our analytic model with 3 wind tunnel simulations of Milky Way-like galaxies impacted by a constant ICM wind. From left to right, they are a low-density, low-velocity wind, a high-density, low-velocity wind, and a high-density, high-velocity wind. In the paper, we focus on 3 well-separated regions above the disk, denoted by colored lines in this figure. First, we compare the gas in our tails to our analytic prescription using the velocity FICM plots shown here and find excellent agreement. Each column is a different simulation and the rows show different times. The black line is our analytic model, and in color you can see the gas from the simulation. I will highlight 2 regions that are not well fit by our model. First, in our low velocity runs, some gas has low or negative velocities at high ICM fraction. This is due to gas that shifts into the shadow of the disk and can therefore fall back. Second, at early times in our high velocity wind, tail gas doesn't reach the ICM inflow velocity. This is due to a bow shock deflecting the wind. With my last minute, I want to show one more result from the paper. What mixing actually does to the stripped gas. Does it destroy dense gas or does it allow dense gas growth? And to see this, we look at all of the gas in the box. And here I'll focus on the solid lines, which show mass versus time. In blue, we see mostly dense gas, or have ICM fractions below 0.5 in a cell. In green, we see the mass of dense gas. In the high density, high velocity simulation here, we see that at early times, as gas from the ICM begins to mix with galactic gas, the mass of low ICM fraction gas increases. Then as mixing continues and the ICM fraction goes above our threshold of 0.5, that mass decreases. In green, we can see the dense gas mass decreases throughout the simulation. Mixing is destroying dense gas. However, in the high density, low velocity simulation in the middle panel, we see a different story. The solid blue, mostly galactic gas line shows the increase followed by decrease that indicates continued mixing and that we see in all of our simulations. But the green dense gas line increases beyond the blue line, and it doesn't decrease again until gas begins to leave the simulated box. Here, mixing seems to drive dense gas formation. The low density, low velocity case on the left may be a bit more complicated, so I'll send you to the paper for that explanation. So here, I've shown you 2 highlights from our paper. First, a mixing driven acceleration model well describes ram pressure stripped tails. And second, depending on ICM wind parameters, mixing can drive dense gas destruction or dense gas growth. Thanks.